Edison three-wire circuits. Edison three-wire circuits are a special type of circuit that gives us higher efficiencies due to lower line loss and line drop. Let's take a look at very quickly how we do the calculation. This is what a Edison three-wire looks like. It doesn't have to be a DC source. It could be an AC source, but since Edison first developed it, it's usually referred only to as a DC. There's two DC sources. They're equal in voltage. And typically in North America, that would be 120 volt and 120 volt. They're connected in series, which means that the source voltage should add together to give us 240. And what we have is 3 conductors that come off. In most of these three-wire calculations, we're going to find that there is a small amount of resistance in each one of the conductors. And the reason for that is to ensure that we account for the resistance of the conductors. So there's our equal voltage source. This is our conductor resistance, represented by our little resistor symbols. And then we have our individual loads. I'm just going to provide 2 loads here. This is my neutral going back. And we know the neutral, its purpose is it carries the unbalanced current. Carries that unbalanced current between the 2 loads. So we'll just name this load 1, load 2, line 1, neutral, and line 2. All right, so what are the steps involved to calculate the voltage across my 2 loads? Well, first thing we have to do is assign a value of current, and I'm going to choose a value of current of, let's say, 20 amps and 8 amps, 20 amps and 8 amps. And the resistance I'm going to choose is very small, 0.1 ohms for each one of my conductors. So there's a few steps that we can use all the time, every time with a three-wire Edison circuit. The first one being, if you are not given it already, assign the polarity of source. So if you have not been given the source and where its negative and positive terminals are, you decide that yourself. I have already determined that here, but I'm just going to put it in a little bit more obviously, like this. Great. Second step. We are going to indicate current flow in our conductors. Okay, so we are going to indicate current flow in, and I'm going to say L1 and L2. So first thing we do, we take a look at our 20 amps and our 8 amps. We're using electron flow theory, so it means 20 amps is flowing out here. So let's put in a little arrow. 20 amps. 20 amps would then flow through here, and then 8 amps would be on the other side of it. So there'd be 8 amps here, and obviously an 8 amps flowing back to my source. Now, at this point, we can start to see where the current value is going to be on the neutral. Because of Kirchhoff's current law, whatever current enters into this junction here must also leave it. So 20 amps flows from my first load to this junction, 8 leaves magically. So that would mean that the neutral current would be 20 minus 8. And that brings us to our third step. We are now going to work out current on the neutral. So we work out the current on the neutral, and we said for this situation, the current on the neutral is 20 minus 8 amps because that carries the unbalanced current. So 20 minus 8 gives us a value of current on the neutral of 12 amps. Now that's not completely done, is it? Because we need to know exactly what direction is that current flowing. And so when we look at the 20 amps and the 8 amps here, 20 is flowing in here, 8 is leaving, which means the 12 must be traveling this direction. So I'm going to indicate that with an arrow. The arrow is important because of the next step. Step 4. Indicate polarity. Polarity across all components. Polarity across all components. Okay, so negative is here. That means wherever the current enters an object, it is more negative, always. Negative, positive. On this load here, negative, positive. On this load here, negative, positive. On this resistor, negative, positive. Wherever the current enters into an object, it is more negative. And finally, we get to the neutral conductor. Again, direction of current flow indicates polarity, negative, positive. Okay, final step, well, almost final. Step 5, calculate line drop. So calculating line drop is simply going to be calculating the voltage that is dropped across each one of these conductors. Since we've got a really small value of ohms, all we're doing is using Ohm's law, right? We're using Ohm's law, and we're using E is equal to I times R. So that means I times R, 20 times 0.1 gives me 2 volts. 12 times 0.1 gives me 1.2 volts. And 8 times 0.1 gives me 0.8 volts. Okay, so now we want to finally get to that step to calculate the load voltages. Calculate load voltages. How are we going to do that? Well, we are going to do it in loops. And the loops are going to take into account all of the polarities along its path. So the first loop I am going to do, I'm going to follow a loop that starts right here on the positive side of my source. And it's going to go all the way across here and back to the place that it started. Now, what is that voltage? How are they all going to work? Well, the purpose in doing a loop is to account for every single polarity. So let me show you how that works. I'm going to start here. The first polarity that we indicate or encounter across a component is going to then be used as the polarity for the component. So this is positive 120 volts. So I'm going to do this. plus 120 volts. I come along the top here, minus 2 volts. I come along the back here. This is what I'm attempting to calculate. We don't know this yet, so we continue on. Negative 1.2 volts. I take all three of these voltages, 120 minus 2 minus 1.2, gives me 116.8. This is the voltage of load 1. Which is right here, 116.8 volts. All right, let's do a second loop. And the second loop is going to be for my smaller load. I'm going to, again, start on the positive side of my source, go all the way around, and return to the same place. So with this one, I'm starting here. The first polarity I encounter is positive 120. So I'll just do it down here. Positive 120 volts. I come along the top. First polarity I encounter is positive 1.2. I come along the back side here. I don't know this load yet. We're trying to calculate it, but down here, minus 0.8. So 120 volts plus 1.2 minus 0.8 gives me 120.4 volts, and that would be load 2. These 6 steps you can use every time to calculate an Edison 3-wire and its unknown values. You have to use these steps in order to indicate the direction of current flow on the neutral so that the polarity is accurate, so that when it is used to calculate the load voltages, it reflects what would happen in reality. What happens in a Edison 3-wire circuit when we lose different components? So let's look at a situation like this. I'm going to omit the line resistance. And with that, I am just going to indicate 5 amps and 15 amps. If we were to lose one of these conductors, which one would be the worst case scenario? If I were to lose, let's say, there's L1, there's L2, and there's neutral. So if we broke line 1, what would happen? If we broke line 1, well, 5 amp load would stop working. Not very dangerous. Or de-energize. 15 amp load would continue to operate, wouldn't it? So 15 amp load continues. What if we were to break line 2 instead? That would be down here. Well, then the 15 amp load would stop. And the 5 amp would continue to operate. So in both these situations, breaking line 1 or line 2 isn't a really massive, horrible problem. All that happens is that whichever load is connected to that line conductor ceases to operate, it de-energizes, and then the neutral would carry the remaining load, which means if L1 broke, 15 amps would be flowing through the neutral and down here. If L2 broke, only 5 amps would be flowing through the neutral. What if we were to break the neutral? If we were to break the neutral, this is considered a very bad situation. Why is this a bad situation? Well, the reason it's a bad situation is that as soon as we do that, the two loads, the voltages across them will now change, and we may end up with voltages that are very high across one of the loads. So the voltages across the loads changes. And the significance of this is that it's possible we may over voltage a load. Which of course leads to damage. So how do we deal with a broken neutral? Well, a broken neutral requires us to have a general understanding of the properties within the circuit. And remember, in a circuit, that the one variable or component that we're measuring that won't change is the resistance. So here is a 3-wire circuit. We have 120 volts, of course, as our source voltages. We have 0.1 ohm resistance for each one of our conductors. And I have a 25 amp and a 2 amp load. Now, when the neutral breaks, same steps I have to go through. So we'll just put a caption on here. Broken neutral. First step, calculate voltage across the loads with intact neutral. So we'll say neutral intact. Second step will be to calculate the resistance of the loads. And the third step will be to place loads in new 240 volt series circuit. So very quickly, let's go through the process. What are we going to need to do? We already know the process required if we want to calculate the voltages across the loads in a intact 3-wire system. In this one here, we're going to break the neutral, but the first step is to calculate the volt across the loads with the neutral intact. So first step, indicate polarity. Indicate polarity across every one of the devices that we can. At this point, I cannot do it on the neutral. Next point, indicate current flow direction. 25 amps, 2 amps. 25 and 2 means that we have 23 amps, and the 23 amps has to be traveling in this direction. That means that the polarity of my neutral should look like this. Voltage drop across each of the conductors, 2.5 volts. Whoop, 23 amps. 2.3 volts, 0.2 volts. Voltage across my first load. So voltage across this load here is going to be, so with intact, so I'll just say intact neutral. I have plus 120 minus 2.5 minus 2.3. So 120 minus 2.5 minus 2.3 equals 115.2 volts. That's for my 25 amp load. On the other side, for my 2 amp load, I have plus 120 plus 2.3 minus 0.2. So 120 plus 2.3 minus 0.2 gives me 122.1 volts. Okay, so we've done the first step. Second step, calculate the ohms of the loads. The ohms of the loads, and I'm just going to label them now. I'm going to say load A and load B. Load A, R is equal to E over I, which means 115.2 volts divided by 25. 4.608 ohms. Load B, R is equal to E over I, which means the current and the voltage. So we have 122.1 volts divided by 2 amps. 61.05 ohms. All right, I've calculated the ohms of the loads. Now we place loads in a new 240 volt series circuit. So what happens when we break the neutral is we end up with a situation like this. Don't forget about the line conductors. $120 volt. 120 volt gives me a source voltage of 240 volts. The resistance value we have is 0.1 of an ohm. 0.1 of an ohm. 4.608 ohms and 61.05 ohms. At this point, it's a series circuit. So if we want to know what the voltage is across each of these, the easiest method is for us to work out the total resistance, and then using the source voltage and the resistance, we can work out the source current. So our total of a series circuit is adding all of these values together. So 0.1 plus 4.608 plus 61.05 plus 0.1. So I'm adding all 4 of these together. I get 65.858 ohms. Total current of this circuit is going to be the source voltage, 240 volts, divided by the total resistance. So 240 divided by 65.858. I get 3.64 amps. Finally, last step, calculate the voltage across each of these. So you could place that, you could use that as your final step. Volt, or calculate volts. So I'm going to say calculate new load volt. So Ohm's law again, right? E, or voltage, is equal to the current times the resistance. So that means that the voltage across this resistor here is equal to the current multiplied by the ohms. So 3.64 times 4.608 gives me 16.79 volts. The voltage across my second load is the amps multiplied by the ohms. So 3.64 times 61.05, 222.22 volts. Which of the two loads will fail? Well, obviously, the load with the larger resistance will get the larger voltage. And that means that when we're looking up here, the 2 amp load, or load B, is the one that would fail because it's getting now almost double the voltage of the original circuit. So I hope this gave you a good reminder or review of how to calculate a broken neutral within an Edison 3-wire circuit. Broken neutrals are the worst. You do not want to have that situation, especially in a house, because everything will fry connected to one of those loads, right? Or one of those line conductors. So why am I drawing a person? It's a great question, and I think it's simply because I can.